Alpha particles are tiny, fast-moving particles released by some atoms. Imagine them as minuscule bullets ejected from the nucleus, the atom's core. They carry a positive electrical charge similar to the electricity that makes your hair stand on end. This positive charge is key to understanding how alpha particles behave and interact with their surroundings. Their journey, however, is short-lived. Due to their charge and relatively large size, alpha particles interact strongly with matter and lose energy quickly. They can only travel a short distance through the air and are easily stopped by a sheet of paper or even the outer layer of our skin. Despite their limited range, alpha particles are powerful agents of change at the atomic level. Their discovery revolutionized our understanding of the atom and radioactivity. Today, alpha particles are not just objects of scientific curiosity. They play significant roles in various fields, from medicine to smoke detection. The story of alpha particles began with the groundbreaking work of physicist Henri Becquerel in 1896. Becquerel, a French physicist, was initially interested in the properties of phosphorescent materials, which glow after being exposed to light. His curiosity led him to experiment with uranium salts, a substance known for its unique properties. While investigating the properties of uranium salts, Becquerel stumbled upon a mysterious phenomenon. The salts emitted invisible rays that could fog photographic plates. This unexpected discovery was made when he placed the uranium salts on a photographic plate wrapped in black paper, expecting the salts to absorb sunlight and emit X-rays. To his surprise, even without sunlight, the plates were fogged, indicating the emission of some form of radiation. This accidental discovery marked the birth of nuclear physics and opened a new window into the unseen world of atoms. It was a pivotal moment that challenged existing scientific understanding and paved the way for future research into the atomic realm. 2 years later, Marie Curie, a pioneering scientist, delved deeper into this enigmatic radiation. Alongside her husband Pierre Curie, she embarked on a rigorous investigation to understand the nature of these mysterious rays. She coined the term radioactivity to describe the spontaneous emission of these invisible rays from certain elements, including uranium and thorium. Her meticulous research involved isolating radioactive elements and measuring their properties, which was a monumental task given the limited technology of the time. Curie's relentless research led to the identification of 2 more radioactive elements: polonium, named after her native Poland, and radium. These discoveries were groundbreaking and earned her 2 Nobel Prizes, making her the first person to receive the prestigious award in 2 different scientific fields. In 1899, Ernest Rutherford, a physicist working at McGill University in Canada, entered the scene. Rutherford, often referred to as the father of nuclear physics, was intrigued by the findings of Becquerel and the Curies. He designed elegant experiments to study the nature of radioactive emissions. His approach was methodical and innovative, involving the use of magnetic and electric fields to analyze the behavior of these emissions. By passing these emissions through a magnetic field, Rutherford observed that they were deflected in different directions. This deflection was a crucial observation, as it suggested that the emissions were not uniform, but consisted of different types of particles. This deflection indicated that the emissions consisted of particles with different charges. Rutherford identified 3 distinct types of radiation: alpha particles, which were positively charged, beta particles, which were negatively charged, and gamma rays, which were neutral. Rutherford named the positively charged particles alpha rays, later known as alpha particles. His experiments showed that alpha particles were relatively heavy and could be stopped by a sheet of paper, unlike beta particles and gamma rays, which were more penetrating. He further characterized these particles and correctly hypothesized that they were actually helium atoms stripped of their electrons. This was a significant breakthrough, as it provided a deeper understanding of atomic structure and the nature of radioactive decay. His work laid the foundation for our modern understanding of the atom and the nature of radioactivity. Rutherford's discoveries not only advanced the field of nuclear physics, but also had profound implications for chemistry, medicine, and energy production, shaping the scientific landscape of the 20th century and beyond. Alpha particles are like the heavyweights of the subatomic world. They are the big players in the realm of radioactive emissions, known for their substantial mass and size. They are significantly larger and heavier than other types of radioactive emissions, such as beta particles, which are essentially high-speed electrons, and gamma rays, which are high-energy photons that travel at the speed of light. An alpha particle comprises 2 protons and 2 neutrons, giving it a mass number of 4 and an atomic number of 2. This specific combination of subatomic particles makes alpha particles unique in their properties and behavior. This composition makes it identical to the nucleus of a helium atom, or He. Essentially, when an alpha particle is emitted, it is as if a tiny helium nucleus is being released into the environment. Carrying 2 units of positive charge due to the 2 protons, alpha particles are highly ionizing. This high ionization capability means they can cause significant changes in the materials they pass through. This means that as they travel through matter, they interact strongly with atoms, knocking off electrons and creating ions. This process of ionization is crucial in many scientific and industrial applications. This ionization process is the basis for both the beneficial applications and potential hazards of alpha particles. For instance, in smoke detectors, alpha particles help ionize the air, making it possible to detect smoke particles. Despite their relatively large size and charge, alpha particles are not very penetrating. This limited penetration ability means they can be easily stopped by simple barriers. Their journey through matter is short-lived, as they rapidly lose energy through interactions with atoms. This rapid energy loss limits their range and makes them less of a threat compared to other forms of radiation. In the air, they can only travel a few centimeters. This short travel distance is due to their high ionization potential, which causes them to lose energy quickly. A sheet of paper, a layer of clothing, or the outer layer of our skin is sufficient to stop them. This makes alpha particles relatively easy to shield against, reducing their potential harm to humans under normal circumstances. However, if alpha-emitting materials are inhaled or ingested, they can pose significant health risks. Inside the body, their high ionization potential can damage living cells and tissues, leading to serious health issues. On the flip side, this same property is harnessed in medical treatments, such as targeted alpha therapy for cancer, where alpha particles are used to destroy cancer cells with precision. Alpha particles continue to be a subject of extensive research and scientific studies, as understanding their properties and behavior can lead to new advancements in various fields, from medicine to nuclear physics. Section 4. Where do we find alpha particles? Exploring common sources. Alpha particles are constantly being emitted around us, originating from both natural and artificial sources. Understanding these sources is crucial for assessing any potential risks, and for harnessing the power of alpha particles for various applications. One of the primary natural sources is radon gas, a product of the decay of uranium and thorium found in rocks and soil. Radon can seep into homes through cracks in the foundation, posing a health hazard if it accumulates to high levels. Other natural sources include radioactive isotopes present in our environment, such as potassium-40 found in our food, and even our own bodies. Artificial sources of alpha particles include medical and industrial applications. Americium-241, for example, is used in smoke detectors, while radium-223 finds use in treating bone cancer. Nuclear power plants also produce alpha-emitting isotopes, although their release into the environment is carefully controlled under normal operating conditions. Section 5. Alpha particles in action. Applications in various fields. Despite their potential dangers, alpha particles have found numerous applications across various fields, highlighting the dual nature of scientific discoveries. These tiny particles, composed of 2 protons and 2 neutrons, are emitted from the nuclei of certain radioactive elements. Their unique properties have been harnessed in ways that benefit society, demonstrating how science can turn potential hazards into valuable tools. Their properties, which make them hazardous if not handled properly, are also what make them valuable tools in medicine, industry, and research. The high ionizing power of alpha particles means they can cause significant damage to living cells, but this same property is what makes them effective in certain medical treatments and industrial applications. One of the most well-known applications is in smoke detectors. These devices are found in homes and buildings worldwide, providing an essential safety function. Americium-241, an alpha emitter, ionizes the air within the detector, allowing a small current to flow. This radioactive element is carefully contained within the detector, ensuring it poses no risk to the occupants of the building. When smoke enters the detector, it disrupts this current, triggering the alarm. This simple yet effective mechanism has saved countless lives by providing early warning of fires. This life-saving application relies on the high ionizing power of alpha particles and their ability to be easily stopped by smoke particles. The alpha particles' inability to penetrate deeply into materials makes them ideal for this purpose, as they are stopped by the smoke and do not pose a risk to humans. Alpha particles are also used in a specialized type of radiotherapy called unsealed source radiotherapy. This treatment involves the use of radioactive substances that emit alpha particles to target and destroy cancer cells. Radium-223, an alpha emitter, is used to target and destroy cancerous cells in bone metastases, relieving pain and improving quality of life for patients. This treatment is particularly effective for patients with advanced prostate cancer that has spread to the bones. The short range of alpha particles ensures that they deliver their energy to the tumor with minimal damage to surrounding healthy tissues. This precision makes alpha particle therapy a promising option for treating certain types of cancer. In the industrial sector, alpha particles are employed in various measuring and imaging techniques. These applications take advantage of the particles' predictable interactions with matter. For example, they are used in thickness gauges to measure the thickness of thin films and sheets, and in static eliminators to neutralize static electricity in manufacturing processes. These tools are essential in industries where precision and quality control are paramount. These applications rely on the predictable interaction of alpha particles with matter. By understanding how alpha particles behave, scientists and engineers can design devices that harness their properties for practical uses. From ensuring the safety of our homes to advancing medical treatments and improving industrial processes, alpha particles play a crucial role in modern technology.